Sequence capture and dual digest RADseq are two common ways to make reduced representation libraries for next-generation sequencing. Sequence capture uses probes, which I'm showing in yellow, to target and enrich DNA sequences, which I'm showing in black. And because we need probes, sequence capture is expensive because the probes have to be designed and ordered, and we need prior genetic information to know the sequence of the probes. However, sequence capture controls the loci, and there's little missing data, so you really get a good data set for all this effort that you put in. On the other hand, dual digest RADseq sequences DNA fragments that occur between two restriction enzyme cut sites. It's cheap to do on a lot of samples, and there's no prior genetic information needed, but it doesn't control loci, and there's a significant amount of missing data. Because I have so many samples, I thought missing data would be an especially big problem, but I didn't have enough money to use sequence capture. So I set out to develop a new method of collecting genetic data. In collaboration with Travis Glenn, we developed RADcap, which uses elements of sequence capture and dual digest RADseq. And RADcap is cheap, no prior genetic information is needed. It controls the loci, there's little missing data, and it also makes this improvement that sequence capture and dual digest RADseq don't have. It allows me to remove PCR duplicates, and PCR duplicates can give a false confidence can artificially inflate read numbers and give you a false confidence in your genotype calls. So I want to tell you a little bit more about RADcap and how it makes these advantages and how well it works. RADcap is a further reduced representation library. I'm taking RADseq libraries, specifically a variant of dual digest RADseq, which I helped develop called 3RAD, and I'm performing a sequence capture on them. In this graph, I'm showing the number of loci out of all the loci that I designed probes for, how many I retain at different levels of sequencing coverage for a plate of samples. So here are 96 samples, and I'm recovering that many loci. The same plate with RADcap. I've gone up on the y-axis, so I've collected more loci, and I'm going left on the x-axis, so I'm doing it with fewer reads. What this means is I'm reducing missing data, and I don't have to spend as much money on sequencing costs because I'm sequencing fewer reads. And this makes a huge difference when you have thousands of samples. Another way we can look at the amount of missing data in RADcap datasets is to look at the size of the data matrix when we allow different levels of missing data. At 0, I'm throwing away, so this is the percent of loci recovered and the percent of missing data permitted. With 0% missing data, I'm throwing away any locus that doesn't have a SNP call for any individual. At 50% missing data, I'm throwing away loci that have missing data for more than 50% of samples. So that's really a lot of missing data. And what I want you to notice is how flat these lines are from the 50 to 10 or 20% missing data. So it's only when I don't allow any missing data at all that I have this really sharp drop off here. And all of these numbers are non-zero. So the next thing I want to talk about is removing PCR duplicates. Here I'm plotting the percent of PCR duplicates that I sequenced in each of my 28 plates of samples. And lower is better because that means more sequences come from genomic DNA rather than PCR. In about half of my plates, I have less than 10% PCR duplicates, but there's this huge variance. And so the PCR duplicate identifiers that I've incorporated into the libraries are really important to have to identify and be able to remove PCR duplicates.